Hey everyone, and thanks for joining the AstrumDrive podcasts. As usual, we are going to review what we did in the last sprint. So currently we have sprint 8 and we're joined by Nelson. Nelson is the head of our physics department. So Nelson, I know that we did quite a good job in the last sprint. Do you mind just to give us a short overview about the progress we did? It is here on the screen.
Hello, everyone. Sure, Paolo. Okay, let me give you a brief tour about this what we did during the last sprint. We basically explored a lot of nice things, very interesting things, but one of them, most of them, opens a lot of new questions that we have to address now in the future, mostly mathematical questions, in fact. But I can tell you this. Let's do it in more or less in the order that is expressed there. Uh, we work a lot about what is the the way of understanding symmetries in the in any space time, and this is something that you learn when you are studying general relativity. But usually, if you're working with this construction of this word drive metrics, what you do is that you construct the space-time in a certain way, and then you see, okay, I have this space-time, and with this space-time, what is the matter that I need? More or less, that's the way Alcubierre started, and everybody else is doing more or less in this direction. So you need to understand quite well what is this physics that is coming on the metric, the space times that you're constructing. So basically, one of the things there is that you have certain types of observers that are present. We call these observers Eulerian observers. These are free falling observers, and they follow some path in space time. It is called a geodesic. This then you construct the space-time, the metric, such that these observers are like a perpendicular to some slicing of this space-time. So basically, it's like you take several photographs. I think I explained this before, but it's good to explain it again. You take several photographs in several different times, and then each of these photographs, each is just a space, and you have then a superposition of these photographs that gives you how is the time could evolve in this space-time. And this is a way of working when you want to add dynamics in general relativity and making numerical relativity. The point is that this tells you that some vectors that are defined through this path that the observers that you define, which are in free falling, some vectors have to be some specific type of vectors. They have to be perpendicular, for instance, to the space part. And if you need this to be perpendicular, or it's what we call a time-like vector, is means this means some type of symmetry. So, and to explore how these symmetries are in the system, how are they are present or not, is exploring something that is how you change vectors when you move along this path, and vectors that lives on these space-times and these slides of the space that you define. And you do that by doing something that is calculating the Lie derivative of the metric. And when you do that, you obtain a lot of equations. And these equations have like the the unknowns in these equations are functions which are the components of a vector field. And this vector field is called a Killing vector field. Killing is the last name of the guy that worked on this for the first time, or after the guy who worked first. And these Killing vectors tells you basically you can relate this by doing some mathematics with the symmetries of the system, with the conserved quantities of the system, which is of course very important when you study any physical system. So, giving you this, summarizing this, what we learn is how to implement this in some mathematical notebooks and try to extract the information in not so simple metrics. and it's quite hard to do this. It's really challenging, but it's really interesting. So basically, what we are trying to achieve is that you can describe and you know which symmetries you have in the space times, because you construct the space time in such a way that you want these vectors to be this way somehow. So you say you're allowed to have, I mean, timeline vectors or one killing time vector, for instance. And this means that you have your space-time is constructed in a way that you always are moving in time perpendicular to the space that is where you're living. Of course, this is difficult to imagine because the space is three-dimensional, and then you have to think in a four dimension of motion, which is time dimension. Let's call it that way. Anyway, we learn how to implement this in Mathematica. We still have now new questions because it's not an easy task to solve the questions. You don't even know if you can solve the system. It can be, and it happens that you cannot have killing vectors in the system, which means basically not that the system is wrong. It means that you don't have these symmetries in the system. And this thing we are learning how to do in the best way, and we're working on that. But still, we've finished to implement this, how to at least obtain all the equations and separated and classifications using Mathematica, and we carefully check it out with several metrics, several space times, and put a lot of effort to work this out correctly. Also, well, uh, we use this to calculate a very nice example that is for the future, which is using the Friedman-Russell-Walker model, which is the starting point from any cosmological model that we know at this point, at least at the best of my knowledge. And what is interesting about the Friedman-Russell-Walker is that it has some uh, assumptions that are very strong and important and physical assumptions, which leads you to the fact that you have uh, some function that you call the lapse function in the metric is equals to 1 all the time. And this is related to the fact that you expect to have some isotropy in the in this space-time of the Freeman-Russell-Walker uh, uh, metric space-time. So basically, it says that no matter which direction you look, it's always the same. Basically, it's that. But what if this question arises? What if you this is not really as general, because what you can do is like you can change this, but if you assume that you're always looking in another direction and you see the same, or at least pretty much the same, uh, you always have a transformation that can give gives you or directs you to one again. Well, it seems like this is not as general as it looks. And there's a recent article, a couple of years old, that the study that this is not completely true. It is true, but under certain circumstances. And if it's not true, it means that you have some equation of states, which is the relation between pressures and densities, matter, and so on, that is not the one that is commonly known in the community in cosmological calculations. So this is, of course, we're not doing cosmology here, but the space-time defined here is quite in structure pretty much the same or very similar to any warp configuration. It's not the same, but quite similar. So what we did is, okay, let's take a look to what is going on with the lapse function here and put this to in the future, because we haven't yet put this in a word metric, which means that implies that you don't assume anymore that the lapse function is equals to 1 in the word drive metric, which is what people do, as the same as they do in this cosmological Freeman-Russell-Walker cosmological model. But no, just put something that could be that is depending on time, probably just depending on time, or maybe depending on space. or maybe on both. It depends of which are the physical conditions that you're putting into the system, because this is going to tell you how is the relation between servers inside and outside. And it's going to tell you also that there is freedom, there is room for adding more matter in the system, or at least more complicated equations states in the system. And we're aiming in this direction because this is very important. This is what we think complicated the system. This is basically our idea. Complicating the system and not getting these or very simplified versions, and trying to get pushing more realistic physical situation, still not realistic but a bit more and more realistic. It's going to give us more information about why is still we have this problem of negative density energy and all the problems like that that we can solve. And we think uh, that's the right direction. But anyway, we check this, and basically we check this in cosmological model. We haven't checked it in any warp drive configuration yet. This is like a more or less the situation for that is pointing to future work. For the work that we're doing right now, which is the article that we already writing, we're putting together everything. What we did is like we have this spherical warp drive metric, which is a way of writing uh, Alcubierre's or Natarios space-time in a slightly different way. And we obtained already some results that are not completely new, in the sense that are not very fundamentally different to all the others results that we found in the literature, but there are some that are. And we will obtain also that this way of writing, which is not been done before, is more clear to understand symmetries. It's more clear to understand matter that you're adding into the system. It gives you it's a better way of showing what is going on into the system. But we also find out that it's and also it's consistent with Alcubierre and other. And we find out that it's this way of writing remove some uh, constraints that appears in Alcubierre's, which are due to the fact that it's like you are using the right or the best coordinate system to describe the problem. And when you do that and you plug everything together in the right order, and basically I'm summarizing all the tickets that you can see there in the screen, it's like you find that for instance, this is one example that we're going to publish, is that all uh, the physical constraints, which are the energy conditions, all of them except one are fulfilled, with some specific assumptions. But only the strong energy condition has problems, and it's good. It's good because it's telling us a lot more than we thought about the system. We believe, and we're working on putting this together and writing down. But basically, what we're doing is that we did this, and when we have this, and we use, of course, I'm telling this using, for instance, dust as energy momentum tensor. Then we're putting perfect fluid, and then we start also cosmological constant. And now we are looking to we put in the article we're putting specific relations uh, to specific cases. Like for instance, you have the pressure is related in this way to the density and stuff like this. And with that in mind, we basically have like a full characterization of how you describe these systems in this metric, which by the way is interesting because this metric is not connected directly to, for example, Alcubierre. It's not like you take Alcubierre and you say, well, I have my coordinates and I just change the Cartesian coordinates to a map to a spherical coordinates. No, you won't get the you're gonna get something very different not the spherical metric we're proposing. The spherical metric we're proposing comes more from the very basic assumptions that you can make for a metric to a warp metric, which comes from the best article I have read so far about this in the recent years, which is the public article, and they describe how to construct this, and it is quite nice. What are the drawbacks? Well, the drawbacks is like in spherical symmetry like this is we're rechecking this. I'm working again on the killing equation of this metric, but once you start moving faster than light, than the speed of light, you your vectors, this killing field vectors that tells you how the symmetry is, changes, which means that you lost the symmetry. And that's a drawback. That's a drawback because it means that once you're still moving faster than the speed of light, you are not longer describing the system with the metric, the space time that we started with, and we don't know which is it. So we are working out how the symmetry changes and see what can we do with this. But this is for a future work. Right now we have basically in the state of putting together and presenting to the community. Oh, we think this is the best metric to describe a warp situation.
Excellent. Thank you very much, Nelson. And I know that you guys are currently working on the article, and from what I can see, it's going to be ready in the next few weeks, correct?
Yeah, that's correct. That's
Yeah.
correct. We're working very hard, trying to figure out calculating new teams. Yes, very soon.
All right, so this means that soon we will be able to share it with the community. And I know that at the same time you guys are started working on the second article, because in the first article we're just going to show the foundation of our calculations and the warp drive metric, and after that we're going to publish another one discussing the situation when we travel faster than the speed of light and the loss of this symmetry. Is this the right train of thought, Nelson?
Yeah, it's more or less correct. In fact, I can say that we might have three articles. The one that we're working now, and this is thinking ahead a lot. But
Mhm.
if my best guess is that we have this article that we're working now. Now, this in few weeks we will start the publishing procedure. Then we have another article in our heads that is generalizing these lapse functions, which is relaxing conditions on the metrics, basically. So you can have more freedom, more room for more enrich the energy momentum tensors, the matter that you can put in the system, and then from there we can look into the future with a lot more possibilities, because basically it means that we can work on, I don't know, electromagnetic fields, some type of matter, look for dynamics into the matter, which is a very complicated thing. I mean, you construct energy momentum tensors that are by itself, there are fields in the sense of quantum field theory. So they have some dynamics. They can depend on time, which is quite complicated to work on that, because once you put this in Einstein's equations, it's very messy. Uh, but okay, but the point is that you can open the room for all of this, and then you have a lot of branches, situations that you can study, and of course we will start choosing some of them. And the next article that I have come into my mind now is yes, what happens with the motion of this? It's already, I think, a big task. It's not a simple thing to construct some warp drive that you can say evolve in time, meaning that the space-time is going to change from something to another thing depending on the velocity. Because this means that you have a lot of things that depend on time there, give you some nice symmetries, and you have to work with very messy symmetries there. and that's not simple. And I think that by itself is a lot of work. It's quite a contribution probably, and that's what I have in mind for the moment. But this is more or less the path that we're following or that we want to follow. We always have surprises in the middle, which is nice because usually there are good surprises. Even when you get stuck in the calculation, it means that there is something there that you need to learn, and there is something nice there that is going to happen. You're going to learn when you finish the calculations and you finish how you learn how to do the calculations. It's quite exciting, and we're making the first step right now.
And actually, just before we started this recording, we had this conversation about the use of electromagnetic fields with the warp drives and the connection between. So this is something we can definitely explore in the third article. And Nelson, I think we can close for today. Do you have anything else to share or anything else to say?
No, I think no, but the same as usual. Please, if you're listening to this, just like the video, a comment if you wish, if you want to share with us some things that you find in the web, some ideas or whatever you think. It will be very good, very good. If you can support us with money, oh, even better.
Thank you, Nelson. Well, uh, in this case, well, thank you everyone for listening. That if you like the video, please like it, share it. If you feel like supporting us on Patreon, we're sharing the link. And with that, let me wish to all of you to have a very nice and successful week.